Okay, so this tutorial is about symbolical expressions, computer algebraic system, and metaprogramming R. And before I get into this, I want to sort of give you a little bit of example. If you have ever played with symbolical expression before, because R is using the package called Analysis, which is called yet another computer algebra system. I know this might not relate to a lot of contents, but I'm just using this example to bring up the idea of what is the idea of expressions and expressions and the parsing and deparsing of symbolical variables. I could use this to show you that instead of finding finding solutions numerically or just finding things numerically or calculating derivatives numerically, you can get symbolical expressions just like you are using Mathematica or other thing. And instead of storing the value, it stores the expressions in a list-like structure or like a network structure so that the program knows how to derive. And that's pretty cool because, you know, it could take care of your symbolic variable and give you an exact value instead of, and do the deductions instead of just computation, right? So this is pretty cool. It solves x squared minus b0 in the complex form. And it's pretty much all it does. But what's most useful for is probably math modeling. In this case, I'm using my previous code, mathematical modeling for R sample code, to show you how to use R to deduct the formula first, and then evaluate these formulas with a bunch of numbers to sort of get the results the results from your models. And this is important because when you start modeling something, you don't always get expression that you can directly evaluate. Sometimes you have to do some deductions and symbolical work before doing that. And if a computer algebraic system can solve the equation for you, then you could use that expression to deal with later works. And this is probably very useful using probably using some packages as well. I would just download this to make it work locally. So the way it works, you specify such. I mean, you specify such expressions, and you find the you could find the derivatives, and you can like find other find a second derivative, and then you could solve the expressions, and you could do this. Okay, so how does the program actually calculate the derivative? Is a good question because when I get a function here, so I can first start with a function, right? Okay. I could let me just first make sure that I have installed the library. Install packages. Okay. So this is the this is my R project. Okay. And do I have that package? Okay. Oh, sorry. Okay, so maybe this package has changed a little bit, but the idea of expressions it's quite similar. So first, I start with a function, which is nothing, uh, more than just, I should use some silly mistakes here. Okay, so first I start with a function, and from the previous video, all of us know we can calculate such values, but yeah, it's not very surprising. You could calculate the derivative by using numerical values, say put f2.1 minus f2 here, but it's not as elegant because if you look at the components of functions, so the first part, components of functions. If you look at the components of functions, if I instead of printing out f, I just print out the structure of f, right? It says function x squared. But can we actually get access to the value of the function itself? I mean, if two functions define the same mapping, I mean, if I send some variable to two functions and get exactly the same output, same number, same format, same everything, same input, same output, are they the same option? Are they the same functions? I mean, in some cases, they are the same functions because function as long as you have this as long as you have the many to one or one to one mapping, you can create a function. However, it's different because when you type a function into the program, actually the contents of the function is recognizable. Let me show you what this means. So g is also a function of x, but it returns x squared in a fancy way. Well, in the primitive way, x times x. Okay, let's run this function. If I put g here, you can sort of see g is different from x because it's an x times x, right? Maybe in some other language, the compiler will be smart enough to optimize the first one into the second, but it doesn't really matter. There's a function that could let you see inside the function. What's inside the functions? Body of the f. What is the body of f? X times x to the power of 2. What is the body of the function g? X times x. Okay, so f and g are same and different at the same time now, and it really is it's different in some ways, and I could say I could use formals of f. What is formal of f is x, and what is formal of g, right? Still is x. I can define a function that is called h of x that takes in y and put y square as the output. However, the formal of the function h would be different because it's called y. Just because it has a different name, it's a different function. I mean, in computational sense, right? But just like the class operator, we could do other things for that. For example, I want to change f. So let's say body of f is no longer x to the squared. Body of f, we could change the way that it computes, or we could change this completely because we can write such expressions and feed the expression into the function. All right, so the body of f is an expression. I'm using expression there, not a function, not a package, because expression s squared minus 1. And I could say, I could call f2. And it's magically it's going to be 3. It's not magically, it's just somebody defined it to be 3. Okay? And also I can change the formula. I mean, the formulas of f is this, I could call that, maybe we call it list y equals to 1. And it wouldn't, and since I changed the formal, the function is changed. Okay, so oh, okay, so f is not defined, but it doesn't matter. We just want this line. Okay, so the function y equals to 1 x squared minus 1. Now we could change the body of f into an expression y squared minus 1. And it still works, right? Still works. Okay, so that's pretty much what an expression is. However, you could convert things in between. For example, you could have a function called as expression. This is the expression. So if I load the menu for this, it says as expression something, an arbitrary R project, R object. So you could do maybe as expression x cubed minus 2 plus 3, and you can see this is an expression of this. However, there's a big problem. When I get this, I have expression of s squared minus 1. When I put this thing into the expression, it still gives me this, right? So we shouldn't put a quotation mark there so that we can have direct thing, but still x is not defined. So the only way we create like the original way we create the expression is just to use expression. If we want the expression from text, we should use parse and substitute text is, yeah, no, it's strange. Oh, sorry. Just parse text is this, and you get it right because there's no longer other quotation marks. So the output of this function can be used to modify another function. Okay, that seems quite complicated. Let's do it in this way. So f let's define a function called change function. Change the body of the function. Change function body, or just to say maybe I'm playing with systematics. And the first column I have the function, the second I have some texts. Okay, so it changes the function. It returns the function, but it does some modifications to it. So body of the function can be changed into parse text equals to text. Okay, and I have a function. Okay, this is getting interesting. I have a function x squared, and g is change function body at x f. I want to change f to make it 3 minus 2. Okay. Does it work? Does it work? Let's see. It says unexpected symbols in this. So I probably used the wrong syntax. But it's all right. It works. And let's print out g. What is g? It's not magically, but with some method, x cubed minus 2. Similarly, you could change the function argument. But this time with list, okay. Oh no, function formals with a list. I'll just call it L. Formals. So formals is L, and it works similarly. I'm not going to show you this because it's too basic. You could easily throw that out. And there's an interesting function called D. Let's load the menu. It's a symbolic and algorithmic derivative of simple expressions. So, and it belongs to the package called derive, or technically speaking, the derive function in R. But because you don't need to, you actually don't need any function to do this. R has its derive function for you. Yeah. And you could do integration, but integration is complicated. I think R does. Numeric integration. I'm not sure about symbolic ones. So this is the way we derive things. We can given an expression, find its derivative. Y is equal to expression 3 times x plus 2, and probably I derive this with derive. Okay, and y is already an expression with respect to x. Let's see what happens. Okay, already this. Okay, and it gives you another expressions. And it says gradient of x is a 3, right? But it's not, it's not very useful because the output of this is called a dy dx. It's not very helpful, right? So what's the type of dy dx? Still, it's an expression. So if it's an expression, it could be printed in different ways. Let's see, class of dy dx. If you watch the previous video, you'll probably be amazed to see that it's still expression. It's not. There's no. There's no anything special. And that's because some of the functions are already integrated into the R itself. Now, can I evaluate this? Say I have x equals to 3. Okay, x is now 3. right? X is 3. And I can evaluate an expression, evaluate y. Oh, and it tells me y is 11. So 3x plus 2 is 11. Is it right? Yeah. And more importantly, I can evaluate dy over dx. Well, not very, not very elegant. Let's just keep the numeric value of this. No, that's evaluation of y. That's evaluation of we shouldn't. So it should do this attribute gradient. So x is 3. However, this isn't very useful because, like, even if you do evaluation of the expression, it's still going to be quite messy. And there's actually a way to get around this. I'll just say derive something function equal to true. So what's the difference between this and that? I'll actually change this because we don't need two variables. We only want the, in this tutorial, we usually only want the simple case. I want to derive y with respect to x. And notice that derive and d are actually the same function. Same functions? The same group in the same group of functions. Okay. So this is my dy dx too. And I think it's going to turn out nicely. But it gives me as a function. Okay, this is great. And dy dx 2, 3. You know, it's pretty obvious. It's better than the evaluation thing. In a similar way, you could write function to express function. You can write function to derive functions, or to say like solve other functions. But like actually, I think the package called Ryakis has changed a lot of a lot of things. So there's a similar way to do this. Just do YAC. And I can have another question about this. Why is it useful to do this? Why is it useful if I only have a function that takes in a string instead of expressions, and let me sort of do this kind of calculation? Why is it useful? I mean, this is still kind of messy, because if I want to use a symbolical calculation thing in the numerical computational language, I'm going to have a lot of problem with, well, a lot of things, like say defining symbolical variables and a lot of things. This is because even if you have no idea of how these function, I'm not encouraging that. I mean, even if suppose you have no idea how this package works, you could still write a function that converts an expression to a sort of string, and then convert the string output of the system of the API, and sort of convert it back into a string, convert it back into a kind of expression, and this will actually work. For example, let's just say this, and I could do not this. I could convert an expression back to a string very easily, right? So as character y is this. Now then I can use as character y to like sort of simulate the process of getting a character into the form of this. And I'm going to be very careful about my return type. So my return type is going to be expression. Oh, sorry, I should use the quotation marks for that. Okay, and why does it matter? Like, why does it matter? It's now it's an expression. Now it's a Ryaka's expression. Why does it matter? Notice that we haven't done anything yet. We only passed the expression into let's say another program and get another expression out of the program and back into R, and you could evaluate that. But it's not important because we can almost always uh, do sort of a string manipulation. For example, I could solve this. Remember what I did with the web page? I can do this, right? So I'm going to write this in sort of, solve this with respect to R. So let's see what happens. Probably -1. I want a real solution. Okay. Okay, it gets back the value. So it actually solves my equation. So if I write a function like this, like solve expression, right? And it's going to be a function of x and dependent variable. But you could like generalize this further. I can actually give you a sort of hint to so this is my dependent variable, and this is my expression, and this it's a solving function, so that you have made some progress in integrating the solving expressions into R, and I could just use solve y here. Dependence increasing, so I want solve y with respect to x, or expression we could do, and it all works out. I mean, it looks like a native function, but it's actually calling a lot of things. The reason for you to know how this works is that it's not only applied to symbolical calculation and sort of mathematical modeling here. This could apply back to a number of other ways. Let's say, for the sake of calculating derivative, I can do but still this is for math modeling. I can do this kind of optimize